Okay, first speaker is Professor Taekwang Jang from ETH Zürich, Switzerland. He got his BS and MS degrees from KAIST, and then he joined Samsung Electronics and worked there for a while, and then he moved to US for his Ph.D. study at University of Michigan, and then he got Ph.D. there. And then after postdoc, he joined ETH as a professor. Well, he got lots of awards, but let me introduce some of them. He got the IEEE Solid-State Society New Frontier Award in 2024, and he got Outstanding European Paper from ISSCC twice, 2021 and 2022, and he also got Outstanding Forum Speaker Award at ISSCC 2022. And I believe this is when he was a student. He got a IEEE KAIST Award in 2009. Yeah. Okay. Please welcome Professor Jang.
Thank you so much for your warm and kind introduction. And hello, everyone. It's very nice to see you early in the morning on Sunday. So I hope I can make your time worthy. So today I'm introducing circuit ideas that may improve energy efficiency of the analog circuits more significantly compared to the conventional approaches. So I would say that these are not flawless techniques. There's always pros, cons, and different techniques. But at the same time, it's always nice to explore techniques that is not known, but something different, so that can increase the diversity of the field. And then we can also open up a new methodology that can be generally installed for many applications. So first technique I want to introduce is somehow energy efficient amplifier. So there is a little bit of physics behind it. So let me somehow run quickly, but at the same time, let me try to give you the main idea behind it. So let's say there is an amplifier. So the amplifier always have a power and noise trade-off. What that means is that the product of the power consumption and the in-peripheral noise becomes somehow efficiency of the amplifier, meaning if you can make an amplifier consuming less of current while having a small amount of the noise, that is can be seen as a good amplifier, while something else have a very high power consumption but have lots of noise, that is somehow bad amplifier. So the way they define this is somehow introduced by Professor Willis Sanson and then also Steyart. Together they have formulated what's called as a noise efficiency factor. So the way they defined it is to normalize their amplifier's performance to a single BJT. So let me first look at how the single BJT's noise performance is characterized. So all the BJTs, they have in-peripheral noise, but before we calculate that, we need to understand where it comes from. It usually comes from the shot noise from collector to emitter current. So there are many other components, but this collector shot noise is most dominant noise factor inside of the BJT. Then the shot noise is 2 times Q, the electron charge, times the collector current, IC. That product, if I calculate the in-peripheral noise of it, we need to divide the GM square, which is IC over thermal voltage. Then we can calculate this in-peripheral noise spectral density of a single BJT, right? But then if we want to calculate the in-peripheral noise of the BJT VRMS, we need to calculate the spectral density integrated over a certain bandwidth, because if you want to integrate to the infinity, the RMS value also diverges to the infinity, so there's no meaningful information we can get out of it. So what we try to do is define a noiseless filter, low-pass filter, defining the cutoff frequency of our signal bandwidth, F bandwidth, right? What that means is that we can endure up to 3 dB of the signal degradation at this F bandwidth, but then we can somehow get the advantage of the filtered noise shape of this red. But there is a very interesting equivalence that we can exploit to calculate this red shaded area, because from this F bandwidth cutoff frequency, you multiply pi over 2, the fixed constant, then you draw a line there. You can see that this green shaded area and this red shaded area are equal. You can prove it in the integral equations. I wouldn't do it this talk, but what that means is, though, the area of this red complex shape is same as this rectangular shape of this. What that means is I can calculate the inferior noise of this BJT by multiplying spectral density, bandwidth, and then pi over 2. Then this is the noise of the BJT. But what you can see here is that if we burn more current, we can reduce the noise. And if you increase the signal bandwidth, then we are having more noise as a consequence, right? But then in order to understand what is the fundamental noise characteristic of a BJT, we need to normalize this current and frequency dependent factors. So by multiplying this noise with the current and bandwidth, we can get this fundamental noise characteristic of the BJT, and which is pi kT multiplied with the thermal voltage. You can see that everything is, let's say, constant numbers, right? Boltzmann constant, temperature, and the thermal voltage. So as far as we have this fundamental noise characteristic, if you make any amplifier out of BJT, and if you multiply the bandwidth to it, and then divide the current with it, then you can get the RMS noise of the BJT. Then how the noise efficiency factor is defined? That is defined by multiplying the in-peripheral noise with the, let me repeat. So noise efficiency factor is defined by the ratio of the fundamental noise characteristic of the BJT and the noise characteristic of the amplifier that I wanted to use. Meaning, let's say I have an amplifier which has a certain in-peripheral noise given a certain noise bandwidth, and this one has also certain current consumed. By calculating noise characteristic of this amplifier and normalizing with the BJT's fundamental noise characteristic, you can define the noise efficiency factor. There's a funny one-over-square root of 2 term included in this formula. I have to get in detail about why this is included. But anyhow, the concept is maintained. This shows how good my amplifier is compared to a single BJT. Then, of course, lower value is the better. But then if you are calculating this noise efficiency factor of a single MOSFET transistor, so this shows how MOSFET common source amplifier is better or worse compared to the single BJT. Then the single BJT has a single MOSFET has a channel thermal noise, which is calculated as a 4 kT gamma GM. And GM is maximized. GM over ID is maximized when the transistor is working in the subthreshold region, which is why we are calculating NEF there. Because if you're moving away to the strong inversion mode, your NEF gets worse and worse. So if you're looking into the best case, we can calculate the noise efficiency factor when the transistor is in the subthreshold mode, and which is the GM, in which case GM is the ID over NVT, and this gamma is calculated as N over 2. And N here is also called as a subthreshold slope factor, whose value is about 1.2 to 1.5. If you have taken the course of analog IC, this subthreshold slope factor is defined by the capacitance of the oxide in the transistor to the depletion capacitance, right? But anyhow, this by using this formula, we can calculate again the inferior noise of the MOSFET and then noise efficiency factor of the single MOSFET, which is around 1. So this is what people generally believe as a fundamental limit of amplifier in CMOS technologies. The single MOSFET has a fundamental limit of 1 as a noise efficiency factor limit. So if you are using any different combination of these MOSFET transistors to get a certain amplification function, you are using the combination of this noise efficiency factor. What that means is that your noise efficiency factor is always worse than this. Because, for instance, if you're making a differential pair, you use 2 transistors, your noise is doubled because you have 2 noise sources. Your trace conductance is held because it sees 1 over GM of the other source as a source to generation resistance. Then your NEF becomes quickly worse, right? So there are many other topologies that you can think about. but all of them has to be worse than noise efficiency factor of 1. So let's say if you have made your own amplifier in the future and measure the noise efficiency factor, oh, I designed so well, I get the noise efficiency factor of the 0.3, then you have to question yourself, did I do something different compared to GM over ID? If you haven't done that, there probably is a mistake that may indicate a wrong number, right? But anyway, if you make a feedback configuration out of it, so this is what people commonly do. If you make an amplifier, you do not use it correctly because the open loop amplifier is always nonlinear. It has some dynamic range issues, gain variations that you wouldn't want to use this amplifier in the open loop fashion. Then you usually give a passive feedback, for instance, capacity ratio, in a way to accurately define the input to output relationship. Because now relying on the ratio of the components rather than the absolute value of the components, then your precision can be much, much better. So this is what people usually do. In doing so, the major problem is that the noise efficiency factor of the overall circuit, although I wouldn't drive it today, cannot be better than this open loop amplifier alone. It becomes slightly worse than the open loop configuration, meaning our closed loop configuration of the amplifier still suffers from the noise efficiency factor limit of 1. But the question is, I see here as a very accurate and noiseless component in the feedback, which is made out of passive components, and I see a open loop amplifier who's noisy and dirty, but it has a strong drivability that enables such an amplification. Then can we do the opposite? Can we use the passive circuits that is accurate and low noise as my main amplifier? And then if there's any issues related to the operation of it, can we use any active feedback to compensate for it? Then if we do that, what will be the role of it? That's somehow the question that we wanted to answer. And the way to make a passive amplification is not so much difficult. This idea has been used in many power converter domains. If you want to do the power conversion from 1 volt to 2 volt, 1 volt to 3 volt, you can use the switched capacitor, and the mechanism is very, very simple. You can get the multiple capacitors first in parallel, and then you serialize them to get the amplification factor of the voltage by the number of capacitor. So if you use the 2 of them, as shown in this figure, then you get to get the amplification factor of 2. If you use the multiple units, n units in parallel, then you can get the amplification factor by n. Right? So that, let's say we have done it. Then how does it operate? The first issue that I'm seeing here is that when the capacitors are working in parallel to sample the input, the output P node, which is connected to switch 2, this is disconnected. Of course, the output is not driven yet, so it's floated. But we cannot allow this for the continuous domain amplifiers. So what we can do is we can use 2 units of them working in parallel. One has a Phi1 as a sampling, while the other one has a Phi1 as the amplification. So it's somehow ping-pong operation in a way that one is driving the output P, the other one is sampling, and then this one is driving the output P, then first one, this one is sampling the input. If you are ping-ponging this, then you always continue to drive the VLP. The second problem that you see if we do that is that this V in N is always connected to the V out N, meaning this small magnitude is always connected to the output, while this output P is the amplified version of the voltage difference of those two. Meaning, even though you do not have any input common mode fluctuation, if you see the output average of those two, it has a common mode fluctuation. This is not very good for accurate amplifiers. We need to make our amplifier that is common mode resilient. The way we can do it is, again, use this 1 SP cells in parallel. So we use 2 of them now. One, we receive V in P in the positive terminal to amplify it and get a V out P here. And the other one, we swap the input. So then V out P is now equivalent to the negative terminal of the amplified version. So we can get the V out N out of it. Then we can have a common mode free differential output. Let's say if we do it, let's calculate the noise efficiency factor of the such amplifier. First we need to calculate is the noise of it. Maybe there is a very popular formula of the KT over C. If you sample the noise on the capacitor, the noise power of it is a KT over C. That's somehow integration result of the overall noise. But then, what is the noise spectrum level? That's what we are more interested in, because after we do this type of the switched capacitor amplification, we'll do a one-pole low-pass filtering at the later stages to make it fit into our signal bandwidth. Let's say if we do it, then we need to understand what is the noise level of the sample noise of the KT over C. What is calculated as is the somehow Nyquist rate concept. So if we have a KT over C of the noise, then if you're sampling using a certain frequency, F sample, you're repeating this sampling at every F sample times per second. If you do it, the Nyquist bandwidth of your noise is F sample over 2. Meaning that KT over C noise is spread across this F sample over 2 of the frequency band. So F sample over 2 here, 2 is moved up, meaning KT over C times 2 over F sample is the noise floor amount. But then from here, there is somehow a little residual noise at the high frequency because of we are sample and hold the input signal. That sample and hold signal creates a sync function in the frequency domain, has some rippling noise at high frequency. We don't care because we will anyway low pass filter them. But eventually what you get is by integrating this red noise, assuming a single pole low pass filter at the F bandwidth, you get this formula. It's a little bit complicated, I will not read it. But what's next thing we need to do is calculating a current consumption. So unlike this GM over ID based amplifiers, this switched capacitor based amplifier does not have any quiescent power consumption or quiescent current consumption. So we need to calculate what is somehow parasitic current that we need to consume, which is the power to turn on and off the switches. So because you need to turn on and off the switches to change the configurations, each of them has a gate capacitance of the CP. And you know the also popular formula of how much energy is consumed to turn on and off a one capacitor value of CP, which is C VDD square, right? And the current to drive it is just the capacitance times the VDD. And if you are doing this energy consumption every F sample times per second, the current consumption of this amplifier is C VDD times F sample. This three product becomes the current consumption of this switched capacitor amplifier. What's interesting here is that this plus capacitance is a ratio of the total sampling capacitor. Because when you are sampling analog signal on a capacitor, you have a somehow RC network that is defining how fast it can settle. And this RC time constant has to be shorter than my sampling frequency so that we can really sample the voltage properly and then do the amplification. Otherwise, we get the signal attenuation. So then if you want to have a sufficiently low resistance, you need to increase the gate size. If you increase the gate size, you have a bigger capacitor. So if you have a big capacitor here, in order to reduce the RC time constant, you need a small resistor that is increasing the CP. So big C total increase the CP, meaning we can get a certain ratio between them, which is better. This is also heuristic number because this is technology dependent. If you go to advanced technology node with a very small input capacitance, then you can have a small current, right? And then this is also depending on the sampling frequency that you use. If you have a very fast sampling frequency, you need a big capacitor, meaning beta becomes bigger. So overall, this is somehow one number that I can say, beta equal to 0.01 is approximately what you can find in the 180 nanometer technology when you're doing about 500 kilohertz sampling. Then if I calculate noise efficiency factor of such series parallel switched capacitor amplifier, you can find that NEF can be much lower than 1, meaning this switched capacitor based amplification is much more energy efficient compared to the continuous domain amplification. But then there's a downside of it because we need to have sampled the input using a parallel capacitor, so it increases capacitance loading in the view of the signal source. And then this works not as an active power amplification, this is only voltage amplification, meaning it works as if it's transformer, one-to-n transformer, and transformer has a characteristic of reducing the load impedance in the view of the input node. So let's say if we have a load capacitance of C1, In the view of the input to the transformer, you get the n squared times of the C1, meaning your capacitance seems much bigger, and it has a lower impedance. So your source needs to drive the low impedance load, which is very challenging. At the same time, if you switch the capacitor up and down, it has a bottom plate capacitance, which is a capacitance to the substrate usually, and that alternates from ground to the input, which causes the resistance order of 1 over Fc. So these things all contributed to reducing the preferred impedance, which can be a significant penalty when your signal source has an output resistance that is bigger than these numbers. So the way we handle is not so much difficult as well. So here we have a famous Professor Peter Harp also proposed a technique to solve such challenges, which is using a positive feedback loop. So these are, by looking at the output voltage, we know how much current this input is provided. So by using this positive feedback, you provide this charge actively, so you can cancel it. So if you go back to our original question, let's say we use the passive circuits to amplify the circuit. Would it be the better noise efficiency? Yes. But what's the penalty out of it? And what is the role of the active feedback circuits? The role of the active feedback is the impedance boosting, right? So by doing so, we can have very high input impedance amplifier whose noise efficiency factor is also very good. So this type of amplifier, for the first time, broke the somehow limit of the fundamental, also believed as a fundamental limit of the noise efficiency of the amplifiers. This is power efficiency factor, not the noise efficiency factor, by the way. This is nothing but noise efficiency factor square times VDD. Meaning, if you are, VDD is 1 volt, noise efficiency factor limit is also 1. The multiplication of NF square and the VDD is also 1, right? Meaning, so you have a fundamental limit around 1 as well here. But then they can go very low. So although I show about 0.45 in the calculation, some other prior work achieved also 0.26 using more advanced technology now. And then it has many other characteristics. What's most interesting to me is the flicker noise-free operation, because now we use the transistor only for the switches, not for the amplifiers. It's now free from the flicker noise that is produced by the circuit, so that we can see very low flicker noise even below the 1 Hertz here. Okay, so let me go to the second topic. This is also very simple and effective technique where we have a resistive sensing front end. So let's say we want to sense the pressure, temperature, we want to sense any accelerations. There are many types of sensors, one of which is the resistive sensors. These some physical, biomedical information is now converted into the resistor value of a sensor, and then we need to read out the resistance value to sense what was the signal in the end, right? But then what's very common in analyzing this is the resistor bridge. We just have 3 known resistors. Let's say we have 1 sensor. The voltage ratio, so voltage division ratio established by these 2 resistors gives our resistance to voltage conversion. And then if you look at this resistor bridge, there are very essential components in it. First, the current flowing through this sensing resistor is unavoidable because we need to give some power to it to read out any information, right, from it. And then this capacitor needs to be sufficiently large enough because this capacitor defines KT over C noise, the noise that we are reading out from this circuit. So if you want to have a certain precision, you need a sufficiently big capacitor. And the other branch on the left, although it looks unmeaningful, we need them for ensuring the stability and robustness. There is always some noise on supply voltage. There's always some interferences in terms of the common mode fluctuation due to the resistance value, inaccuracy, or any other parameters. So this branch is somehow giving a reference that is fluctuating together with the interference so that we can only get the accurate resistance ratio. But if you look carefully, these 2 bottom resistors are not contributing any information to the sense the result, but they just only consume power. This is fixed resistor burning power, which does not seem necessary. So is it possible to eliminate them, right? So what people usually do in this resistor bridge is duty cycling, because the resistive sensors are typically has a value range of on the order of few hundreds ohm. and then they consume order of milliwatt of the power. But many wireless sensing devices are having the power consumption limit of order of microwatt or even sub-microwatt. What that means is that we cannot always continuously turn on this bridge. At the same time, we do not need the power signal that often. We can get every 100 millisecond, every 10 millisecond, that's sometimes more than enough. What that means is we can always duty cycle it. We can turn off the resistor so we do not burn power. If you need to read out the signal, we'll turn it up briefly and get the voltage settled on these two capacitor nodes, and sample the voltage and just turn it up back again. If you do this duty cycle operation, these two voltages initially start from the zero and then settles to the certain level, and then the difference is settled after some tau times away. So what people usually do is, because we need to get the accurate numbers here, so we settle the RC bridge until 6 tau, 7 tau, 8 tau amount of the time, when the gradual slope becomes very, very gradual. So even though you have jitter in sampling that, we are not affected to it. So then you can get the accurate sampled voltage. But if you do it, there is a large amount of the power that is continuously burned by these bottom resistors. And there are ways, okay, can we just eliminate these resistors? And although we thought we are the first one doing that, almost always you have someone who already done it, right? So this work proposed by the postdoc in 2022. They have exactly the idea where the one resistor somehow creates RC settling of this resistor to the capacitor, the other resistor to the capacitor, so that they are settling down. And if you sample after a certain amount of time, you get the voltage difference that is proportional to the resistance difference. And this work from Sungkyunkwan University, they also have done a similar technique, but there are some downside. Rather than explain in detail of this prior work, I will just explain this one back again. So from the original Wisdom bridge, we have two bottom resistors removed. So these two nodes that's connected to the VDD will settle all the way to the VDD after a certain amount of time. In doing so, these two go through a different RC time constant because two resistors are slightly different, and that results in a certain voltage difference at a certain timing, setting time away, which is about 1 tau away. The voltage difference becomes maximum, and then in the end it goes back to the zero again because both of them are settling to the VDD. One good aspect out of it is that at the time when this voltage difference is maximum, the gradient of the slope becomes zero, meaning even though you have the jitter, you wouldn't get much voltage noise. So this type of the RC settling can be also resilient to the jitter. And then if you compare the power efficiency of those two, the gain is bigger by using the RC bridge. Energy consumption is 5 times lower by using the RC bridge. Overall, you get more than 10x improvement in terms of the energy efficiency in the bridge if you calculate that by energy consumption to the SNR. So what that means is the RC bridge can be much more effective way compared to the Wisdom bridge. If you are comparing with the full bridge, of course, full bridge, you can use 4 sensors if you are using a Wisdom bridge, but RC bridge are limited to only 2 resistors. So even though we have the penalty of using only 2 resistors, which is also good for the integration perspective because you need to also only include 2 sensors instead of 4, but still comparing to the full bridge of using 4 sensors, the RC bridge is about 2.5 times more energy efficient. So meaning I believe the RC bridge is actually a better way if you're looking into the resistance to voltage conversion applications. Then this is somehow comparison result built out of this bridge. So these are all the resistance to voltage converter, these are converters. So you can see that this work achieved about 0.3 picojoule per conversion step, which is about 10x better than the state of the art, which is actually goes with the SNR energy efficiency improvement, right? And then there are also a different comparison we performed using only 2 sensors with a less sensitivity, but still this is more than 5 times better. Okay, next topic I want to introduce is the energy efficient LC bridge. Now this is some capacitive sensor. There are some other brands of the sensor that is using the capacitance change. The one most popular probably is the acoustic sensors, that is using MEMS microphone. When there's acoustic wave hits the surface, its capacitance varies slightly. And that is sensed by the readout circuit to transform the acoustic wave into the digital code, right? In the end. But then there are many conventional capacitance to digital converters that is using hard switching of the capacitors. Basic mechanism is that we charge this sensing capacitor with the fixed voltage. And then the total amount of the charge is proportional to the capacitance value, and we try to read out this capacitance, this charge, to understand what the capacitance is. In doing so, there is actually a better way we propose here, which is using the Resonant LC bridge. So first mechanism is that we have a certain capacitor, we pull it to the ground so that the voltage on the capacitor goes down, and then release it. What happens is that if you put an inductor there, it somehow resonates, and eventually if you settle it perpetually, this voltage is becoming equal to the VCM. Then just amplitude becomes zero. This is somehow nothing but a LC resonance whose amplitude goes zero. It's exactly the same as if you have a pendulum, it swings and goes to zero amplitude in the end. But then, if you change the capacitance a little bit, what's interesting is frequency changes a little. If you sample at a specific time point where it was supposed to be the zero crossing point, as the frequency changes, the sampled voltage is slightly different. And that voltage is now a function of our signal, CM, and we can read out the voltage as a function of the capacitance change. If your capacitance becomes even smaller, the frequency gets faster, you get the higher voltage. So this can be working as a capacitance to voltage converter. What's very interesting is, if your inductor and capacitor value are small, the frequency becomes very high, meaning this slope becomes very, very steep. So even with the slight change of the capacitance value, that changes slight timing here, but because the slope becomes very, very fast, so you can get a very large voltage out of it. That means it can become a very efficient capacitance to voltage converter. So if you look at this mechanism, let's say we have a one reference LC oscillator, which always generate the same frequency. So if you delay a certain amount, you always sample the same voltage. And then this one has a signal LC bridge whose sampled voltage is a function of the capacitance value. Then both amplitude goes dying out to the VCM, right? But then if you look at the time domain difference, if you are resonating more and more and more, the time difference of these two zero crossing points becomes further and further away, meaning you get the somehow signal amplification. At the same time, our amplitude gets smaller and smaller. This voltage domain reduction also reduces our signal gain. Then product of this time domain amplification and voltage domain attenuation becomes our overall gain. That gives us the ideal optimum cycle index where we can maximize our capacitance to voltage conversion. And this is happen to be very simple and effective. So these are some arrows are sampled voltages. And shows a very simple and cute formula of Q factor divided by pi cycle is the ideal sampling point. So let's say Q is about 40, then you want to sample about 10 cycles later, right? So in doing so, we achieve the CVC resolution of about 33 attofarad, which is very good compared to the prior Rs, and have a very good SNR and SNDR overall. So this somehow resonant LC bridge can be also a very effective technique. Final topic I want to introduce is some PLL-XO co-design. This is what I see as a current state-of-the-art frequency synthesis architecture and research. So there are many interesting PLL design techniques, subsampling, injection locked frequency multipliers. They achieve extremely good noise levels, order of a few tens of femtosecond RMS. This is extremely small number. So considering how much distance can light travel with this order of few tens of femtosecond RMS, right? That is order of micrometers, right? What that means is that we are generating time and resolution that is order of light travels order of micrometers, right? So this is very, very accurate, but people are doing this while consuming only a few milliwatt these days. But what's the problem to me is that these PLL are extremely energy efficient and low noise. They are tested using external XO or crystal oscillators or devices consuming over hundreds of the milliwatts. So, of course, there are some other solutions of the more energy efficient ways, but still they are not looking into the way of co-optimizing crystal oscillator noise and PLL noise together in a way to get the holistic optimization of the crystal and PLL together. But then why this is high power consumption? Because we want to generate the ultra low noise reference that needs to burn a lot of power in the driver circuit of the crystal. The crystal is also a very, very high Q resonator. If you want to keep resonating at a certain frequency, you need to keep inject the signal, meaning you need to burn power for it. But they have noise of the injection circuit, so if you need to burn a lot of power in the driver circuit in a way to reduce the noise. That's the somewhat critical reason. But then is there any way we can design the PLL-XO together in a way that PLL provides a more noise efficient and a low power driver circuit? And as a consequence, if you get the ultra low noise reference for the PLL, we can use it to get the good output signals. So this is what we wanted to do. And by doing so, we could do more of a holistic optimization as the crystal and PLL together. In order to understand this concept, we need to understand also called as Professor Ali Hajimiri's and Thomas Lee's impulse sensitivity functions. What they proved is that the noise of the electrical oscillator is not going through the time invariant transfer function. So let's say we have a current noise that is injected to the crystal. This is somehow the noise of our driver circuit. Rather than this noise going through a linear time invariant transfer function was really common for us, and we like such a linear time invariant equations, but they actually go through the time dependent transfer function. So let's say if this impulse of the noise is happened to injected when the oscillation waveform is at the peak, this only changes the voltage, and then timing is not perturbed. Meaning, if you anyway just use the buffers to only get the zero crossing time moment as a reference to the PLL, this will not be affected by the noise. At the same time, if this noise is injected around the zero crossing point, then this one changes the phase, does not change the amplitude. This is the problem because what we care about is timing. So this, if you look at this current noise to the jitter transfer function, when the voltage is at the peak or valley point, the transfer function gain is small. When this is close to the zero crossing point, the gain is big. Meaning this noise is going through this time varying gain in converting the current noise into the jitter value. And this is always better to inject something in the peak and valley point. Because if our driver is trying to restore the amplitude, then it is injecting signal as well as the noise. And this noise, if this is applied at the peak and valley point of our voltage signal, then this one does not decrease the phase noise much, right? But then current implementation of the crystal oscillator uses somehow pierced drivers. This is some inverter that is taking the timing of the VP, and by injecting the other side after the inversion, it creates a negative impedance. And amount of the current injected is limited by the resistor. What's bad about this type of circuit is that the amount of the current gets bigger when the voltage difference between the rail to the oscillation node becomes big, because current flowing to the resistor is V over R. Meaning, around the zero crossing point, we inject the highest current. And around the peak and valley point, we inject only little current. So that we are actively using this worst point in terms of the impulse sensitivity function in a way to inject the current into the crystal oscillator, making overall large phase noise in the crystal. So the integration of the current noise and the impulse sensitivity function becomes very, very big. What we can do instead is the pulse injection. Let's say if these two waveform approaches to the peak and valley point, we quickly enable a short pulse to pull these two nodes to the VDD and ground, and then let it oscillate the half cycle and do that again and do that again. In doing so now, we are injecting the only noise where the crystal waveform is close to the peak and valley point. And then after multiplying this impulse sensitivity function and the injected current, we can get very, very small amount as the integration result, right? That reduces the overall crystal noise a lot. And who generates this narrow pulse? We need a certain timing, very accurate timing and accurate pulse width that needs to be generated. We can use the high frequency PLL output. Because PLL output is very, very low noise, we can count the edges. We use the clean edges of the PLL to define these pulses, and we can get a pretty good noise. And then this good noise point is not only good for noise, it is also good for the power consumption. Because in the conventional circuit, the power consumption is calculated as a voltage across it and the current flowing through this resistor. When the voltage is big, current is big. So multiplication of the voltage and current becomes big. So you put a lot of power overhead in this resistor in a way that overall injection efficiency, power burned by this circuit versus the power injected into this crystal, that ratio cannot be more than 40%. So you are wasting a lot of power in the driver circuit. Instead, if you're driving at the peak and valley point, this driver sees only little voltage difference between the waveform to the VDD. So the voltage across this driver is small, and the injection efficiency becomes very good. So you can achieve more than 90% of the injection efficiency, so that your noise efficiency and power efficiency both can be very, very good. So this is some overall comparison between these two types of the drivers. What's interesting here is that the PLL, if you have a noise, you have somehow timing differences in terms of when you are pulling this crystal waveform to the VDD. If you are doing it slightly later, then you will pulling it to the VDD sometime later, and they go through different curves of the transition, and you create a jitter in the end. This mechanism is now the noise production mechanism inside of this pulse injection driver, and you can see that this equation, the PLL noise is added with the 20 log of 10 of sine theta, where sine theta is the phase adder compared to the really peak point where you're injecting to. So if you have it injecting anyway close to the zero gradient point, even though you have a jitter, again, you're pulling to the same level, right? So by fine selecting where you're injecting it, you can reduce this value a lot, meaning even though your PLL has a jitter, XO noise can be very, very low. Overall, so this is some comparison result. These are some of state-of-the-art PLLs reporting both crystal and the PLL power consumptions. You can see that the XO power is order of hundreds of milliwatt or even on 1 watt of the power. So if you are not counting for the XO power, they are achieving a very, very good noise FOM order of minus 255 to 260, right? But if you're including the crystal power, their FOM becomes quickly worse. While we only burn the crystal power of about 2 milliwatt, so overall, they both achieved a good performance, right? So PLL and XO co-design really works. And this is somehow while consuming the same power, comparing the XO noise, you can see that by using the pulse injection, you can reduce a lot of noise there. So overall, I introduced the 4 simple, very effective techniques. 1, capacitive amplification, resistance to digital converter, capacitance to digital converter, and finally, PLL XO co-design overall achieves order of magnitude efficiency improvements. And there are so many probably open topics for you to study. So looking into something new, something novel, something radically interesting, so we can make our field more interesting for all of us. Yeah, thank you for your attention.
Yeah, thank you, Professor Jang, for the excellent talk. Now we are open for question, but yeah, don't be disappointed about yourself, even if you couldn't understand that much. It's, I think his standard is too high. But yeah, if you have questions, then please raise your hand. Okay, so, would you? Yeah, I could. Yeah.
Hello. Thank you, Professor, for your lecture. I have one question about the feedback loop.
Okay.
The crystal oscillator calling that. That your idea is very interesting. But I have a question in the startup phase. So, for example, we have in the startup, the crystal oscillator noise is quite high, and it generates the higher noise of the PLL. But the higher noise of the PLL, right now we will feedback to the crystal oscillator. And so, as you see, what we see here, that the noise of the PLL will increase the noise of the crystal oscillator. So, it seems like a positive feedback that keep increasing the noise. So that's.
Oh, okay. So there are a few things I need to clarify. First is that this cannot start up, meaning we need a crystal to lock the PLL, and PLL signal is needed to inject the crystal. So what we need to start from is the just conventional Pierce oscillator. First generate reference to PLL, lock the PLL phase, and then switch to the pulse injection mode. So this needs to be done. And second thing, this is also very interesting question. You have some crystal noise that is impacting to the PLL, and PLL noise that is impacting to the crystal. So you have a positive feedback loop in that sense, right? So first thing you can look at here is that this is some log domain, so it's some multiplication in the linear domain, right? So this sine theta is multiplied to the PLL noise in defining the XO noise. Meaning, if this number is very, very small, this becomes a positive feedback loop with a very, very low gain, order of 0.0001. Then it is always stable. So it wouldn't diverge the noise. So if I use the metaphor, it's like you have a sun, it's a really big gravity and very small mass of the Earth, right? Even though it somehow try to fluctuate the sun, so it cannot affect much, right? They will just move together as a mass of only the sun. It seems like the crystal is an extremely high Q factor circuit, order of Q factor tens of thousands, while the PLL has an LC oscillator noise order of Q factor 10 or 220, right? So somehow PLL cannot perturb the XO noise that much.
Thank you, Mr.
Yeah, great, thank you.
Do you have other questions? Okay. Thank you for a nice talk. I'm from Fudan. And could you give us some circuit comment about the SPA?
Okay.
I mean the gain accuracy, especially gain accuracy over PVT variation. Thank you.
Oh, gain variation, this is actually a very nice point because this is nothing but the capacitance ratio. So you are somehow sampling with the inputs and you serialize them, get the output, meaning it's somehow very resilient to the PVT variation because we are relying on the capacitive ratio.
So it's the same as the closed loop amplifier.
I agree. What's different here is that they have an input offset and finite gain error that is still affecting the gain, but SPA does not have that. So I would see that actually better in SPA than the conventional closed amplifiers.
Okay, thank you.
Yeah. And what's even more interesting is that this actually relies on the capacitance ratio, it's in defining 1 to 8. So, but 1 to 8, it wouldn't be exactly 1 to 8, then it will have a little bit of a chip-to-chip mismatch. But this one is nothing but the number of capacitors. Let me correct, it's not the ratio of the capacitors, it's the number of capacitors. Even though, let's say, one capacitor here is slightly smaller than the other one, still you get the gain of 2. It's nothing but the voltage sampled on the capacitor stacked together, meaning this is also resilient to the capacitance variations as well.
What about the parasitic effect then?
Oh, that's a big topic. True. So if you have a bottom plate capacitors that is slightly attenuated gain, and the variation of the bottom plate capacitance affects the gain error. True. But then the good thing about here is first, the plus capacitance is on order of few percent out of this main capacitor. So let's say even though you have a 1% variation here is 0.001% of the main capacitor. So gain variation induced by this is anyway small. And if you are including this positive feedback loop to cancel this parasitic effect, then you are anyway moving away from being affected by the gain error caused by the parasitic capacitance.
Basically, you are assuming the capacitor is much larger than any routing parasitic.
Yeah, base cap is, so usually in the power converter domain, people can easily conclude that if you use a MOM capacitor, this is like a 3 to 5% of the main capacitor. If you use a MIM capacitor, it could be less than 1%.
Because here, I believe most of them are undergraduate students.
Yep.
I ask one question for them.
Please.
So in your talk, you have introduced some non-conventional circuits. So I'm curious how you can develop those ideas, which is quite different from the things in textbook.
I mean, how we can inspire ourselves.
Right.
So there are many things we can do. So diversity is very important. So I would somehow recommend you always expose yourself in the different fields and different people to inspire different concepts. To me, what was also very useful is somehow designing different types of circuits. So my group actually worked in the different fields of analog circuits like the PLL, power convergence, and amplifiers, sensor interfaces. It's a little bit broader than usual groups. I think downside of it is it's very difficult for us to specialize in one field very deeply. So we can be some pioneer of the leading this field of research. But at the same time, good aspect out of doing multiple fields is that we can be inspired by the different fields. And this idea is crossing the border of the fields actually is sometimes very useful. For instance, this switch capacitor amplifier is nothing but a DC-DC conversion circuit. Right? So if you somehow use the idea of different field, sometimes we are trying to do something very new in this field, but your friend working in a different field may come to you and say, hey, this has already been done in our field, and this has pros and cons of this and that. So you can somehow, this can be a good way of inspiring yourself by looking at the different fields.
Please thank Professor Jang again.